Hello, hi everyone. So this week we'll be understanding adversarial search. So till now we have learned about how uninformed search work. We used to have the information about problem itself. Then we moved to informed search, where we used to have information relevant to problem, and that we have leveraged to kind of a guided search. Those are known as a heuristic based or informed search. This week we'll be dealing with a different kind of algorithm called adversarial search. So where we'll have some adversarial situation, and the algorithm itself has to find out an optimal way to find out the solution. So this is what we are going to work out in this week, right? So what kind of so till when when it comes about the AI, game is one of such environment where you used to kind of feed the intelligence and evaluate whether it has learned those things or not. So game is a kind of tool to check whatever the algorithm you have fed it will it work in real environment or not, how much successful it could be. So here for adversarial search we'll be talking about the game problem. So what kind of game we'll be talking about? We'll be talking games is generally sequence of moves, right? So for example, chess I played and someone opponent also played another round. Rules that specify the possible moves. For any games we used to have set of rules, and here it is referring to that rules that specify a payment for each move. So I took a move, should I get a reward or penalty for that? So that is score change is a kind of payment for each move is here referring for, right? Objective is to maximize your payments. We used to have some strategy, we used to have some underlying objective what to do. Should I work for maximizing the scoreboard, or it's okay to let it be scoreboard and defeat the opponent? So this kind of objective you used to have. So these are the four components of a game: sequence of moves, rules that specify what are the possible moves, rules that specify a payment for each move, whatever the score you are getting for each move is the third point. Objective is to maximize your payment. Finally, what we have to do, we have to maximize your payment for each turn. Whatever you are getting in the whole game sequence, till the game is from the game start till the game end, you need to maximize those scores. This is the objective. Now let's discuss about what is the difference between games versus search problems. So here, unpredictable opponent we used to have in games where it was not in for searching problems. So this is something different, and we will also have time limits compared to in searching problem there these kind of things were not there. We used to calculate time complexity, but these are two different things. So here, for example, here only let's say 20 moves will be given, and that either you have to win, lose, or like that. So this is called time limits also will be given for that. Unpredictable opponent, what does that mean? It means that you will be playing with someone called opponent, and his or her behavior you don't know. For example, if I'm talking about human, so you don't know what is the behavior of the people, right? So here what we will do is specifying a move for every possible opponent reply. So you need to also think of for that as well. Let's say chase. So we started, I took a play, I started, I took a move. Let's say I moved one pawn just one step ahead. So I also need to think what opponent will do the next time, so that I should not be my any of the unit should not be killed, or should not be go in a situation from where going back to the game would be difficult. So I need to also think about that. So this is called as an opponent, unpredictable opponent you will have. So see, this is the scenario of two-player game. So opponents took a move. Now it generated a new position. That's a chessboard only. Opponent took a move. You got a new kind of chessboard state. Game over. If yes, then either someone had won or some there is to also draw position situation. If game is not over, what we used to do, we used to generate our successors. and evaluate the value, effectiveness of successor and move the highest value successor. What does that mean? Given the situation, let's say game not over, I'll see the situation, I can see there are three possible moves, and I'll have these three successor. I'll evaluate their effectiveness in terms of how game will move forward, how I'll score further, or I'll kill the opponent's unit. So I evaluate the three successors. The three is given for situation, right? And based on this, the value, I'll take one of them, move to the highest value successor. Then game over. If it is so, then let it be. These are the blue circles are the terminals. If no, then opponent will take the move. This, if you see this loop, no, right? So this is how the game has been played. Two player, this is have been shown. It might be multiple player as well. Game as an adversarial search. Why are you calling it as a game as an adversarial search, and what are the components it will have? So states will be the board configuration. So in this lecture we'll be all talking about chess board in general, right? So states are board configuration. What is the initial state? The board position and which player will move. So this is the initial state. What are the successor function? Successors, you understood what I mean to say. Successor means given the situation, what are the three possibles that we discussed? Maybe 5, maybe 7, whatever. So those situation are the three actions that I can take, and will be the kind of successor function. Return list of move or state pairs which is indicating a legal move and resulting state. Yeah. So successor means resulting state. You have the three actions, and it will be might be initial state was S, and if you take A1, A2 or A3, it will lead to S1, S2 and S3. In mind you have taken all three action, and then you are evaluating the value of S1, S2 and S3. You have went to, right? You are checking S2 is quite good. Then what you will do, you will say, okay, I will take A2 rather than A1 and A3 because the effectiveness of S2 is quite good. From there is a more chance that I will win. Terminal state. Terminal state is whether the game is over or not. This is the terminal state. Last state is known as a terminal state here. So this is what it is referring for. Utility function. What is the utility function? Utility, given a state, how effective or the state is defined by utility function. So I took a move, I went to another state S dash. Let's say I was initially in S, I took an action A, I went to another state S dash, right? So S dash, how much utility it is. So this utility function take S dash and say whether how much utility it is. If it is leading to win situation, win state, it will be +1. If it is lose situation, it will be -1. Otherwise 0. Now you see this is the scenario how game tree is being drawn here, and I'll explain each component one by one. So this is the 2-player game, deterministic turn. So let's say this was a chess board. You can see this is a 3x3 chess board. Sorry, it's a tic-tac-toe. So from here what you'll do, you have to put X. You will be putting X at such a position so that your objective should be maximized, right? So these are the possible situation where you can put. There are 9 possible situation where you can put cross, right? So 3 in the first row, 3 in the second row, and 3 in the last row. So these are the 9 state. Why now minimum 0 has been written? Because the opponent will play another move, and it will put O, or you can call it as 0. What it will try? It will try to minimize your objective. That's why it is called mean. So it will put O at some place where it is putting, wherever it is putting, it will put it there. Then it's like again you will put cross so that to maximize your objective. It will put O to minimize it. And finally these are the terminal state. If you see, if 3, 0 would be in the same column, the second column, then obviously 0 will win, and cross, I was the cross, means you are playing game, you are the cross, you will lose. So that's why the utility would be -1. If it will lead to some situation where neither win nor lose, so which is a draw situation, and you will get 0. In another situation, if you can win 3 cross in a diagonal, if you see, then you will get +1. the computer is max and the opponent is min. So we are here now, the situation is you are playing, it is playing with the perspective of computer. So first it is taking maximum, computer perspective is trying to maximize the objective, then opponent is the minimizing it, that's why it is the mean. So computer's turns, opponent turns, computer's turns, opponent turns, and like finally it will go till leaf node. Leaf node means terminal state you will be reaching. At the leaf nodes, the utility function is employed. At the leaf node, utility function is employed. Big value means good, small value is bad. So that's we already said, right? So let me say at the each leaf node. So finally, where utility function has been called, every time it has been called at the end. But this is not the scenario for few games. This is the tic-tac-toe. But for few scenario used to calculate utility function at each state, you took an action. Finally, you went to some state S dash, and there you calculate utility function. But here only 3 utility values are given: either win, lose, or draw. So that's why it has been calculated at the end only. So what is min max terminology? Let us explain in more depth. Move means a move by both the player. It is not like you took a move, this is a move. No, this is not a move. Move is a pair of ply. Ply means I took a ply, my opponent took a ply, then it is called move. Otherwise it will, if I take or our opponent will take, then it is called ply. But pair of ply is called move. Utility function, the function applied to the leaf node. So finally you will be reaching to where? Leaf node, and the utility function says you have reached to the leaf node. Now what is the effectiveness of the state? Whether you have won, lose, or whether you have won, lose, or you are in the scenario, right? Just a second. Yeah, so utility function we talked about. Now backed up value, what does that mean? This is very important and please try to understand. Backed up values of a max position, the value is largest successor. So you will have this scenario, right? Where is the game, if I have to say? So let's say here you have at the end either you own it, +1 you are getting, and this is the third one situation. So you need to check the backward and which state was good for that, and you need to backed up the situation. You need to give more importance to that state. This is the meaning of backed up. Backed up a max position, the value of its largest successor, you are doing that. Of a mean position, the value of its smallest successor. Similar for this is for max, you have to backing up situation for maximizing the utility function that you are getting, right? And minimizing just reverse for that. Min max procedure, what it does, it is doing this statement: search down the several levels, at the bottom level apply the utility function, back up the values all the way up to the root node, and the node selects the move. So let's understand. Let me enumerate the paragraph. So what is saying, you have now the terminal states, you have reached the scenario, this one. Now you are backing up, you are backing up your parent's node depending on the utility value of terminal state, and it goes like upward till the root node. So this is the meaning of the here min max procedure. It will be more clear once we'll show the example. So this is the situation. Let's say the professor used to give this example. So you have these are the root nodes. You can root leaf nodes. You can see 80, 30, 25, 35, 55, 20, 05, 65, 40, 10, and all those, right? So if it is a min max, what will happen? If then you have to see, you have to back up. So if you see the left one at the bottom, there are two childs 80 and 30. If it is the max one, this stage is the max one, what I'll back up? Should I back up 30 or 80? Obviously I'll back up 80, so 80 will go there if it is the max one. But if it is the mean one, what I'll do, if it is a opponent play, so let's start with the top. I need to check whether it's it should be max or mean. So at the top we'll do max, then mean, then max. Okay, so this, if you see this triangular box, it is conveying the information. If it is upward means max, if it is downward means mean. So here for 80-30 it is saying the mean should be backed up, opponent play. I'll back up 30 rather than 80. For second one, 25 and 35, what I'll back up 25. Then we'll have 30 and 25 in the parents node. In the next, what I'll back up 25. So 25 will be the above one. So see this situation. Sorry, I missed it there. It is the max one, not 25. It will be 30. So 80 and 30 you had at the last node. You are backing the minimum one. It is going 30. Fine. For the other one, you are again doing the minimum one. What is the minimum? 25. Now among 30 and 25, you have to back up what? You don't have to back up minimum, you have to back up maximum, because the upper node or the parents, if you see, this is the upward direction. So I have to back up the maximum one. I am backing up 30. So similarly, if you fill up the whole this breadth, you will get 30, 20, 15 and 16. Now what to do next? You need to see among 30 and 20 what you need to back up. This is the downward, this is the opponent, then I'll back up 20, right? For the second branch, what will be 15 and 16, what I'll have to back up? I'll have to back up 15. So finally we'll have 20 and 15 and I have to take max out of it. So it will be 20. So finally, if computer is the first turn, then it can get 20 at most. So this is how, this scenario just explain like that. Any question, any suggestion, you can let me know. Now let's understand, this was the min max algorithm, what are you doing? It's very clear. So from leaf node we are starting, we are taking it's depend on the mean or max. It's not a fixed rule. So if it is a mean, you are taking mean, then max, then mean, then max, and finally you are reaching the root node, and that root node is the final state, that how much computer can get it. So 20 is the here answer for this problem. So for doing this algorithm, how much time you will take, whether it's optimal or not, complete or not. So this is we need to discuss. What are the properties of minimax algorithm? Okay, so minimax, you can see the term. So at first node, from where you will start roof, it will be first mean, then max, and then you go in that order. Is it complete? What completeness of algorithm means? Completeness of algorithm means, if I'll give you a problem, I'll give you and there used to be some solution, there exists some solution. Will the algorithm find out the solution? This is the meaning of completeness. So minimax algorithm is complete if tree is the finite. If tree is infinite, obviously it will not able to do that much, searching and all those things. There would be constraint for those things. So here, if you see, so what it is saying, is it complete? Yes, it is complete. It will find out a solution if tree is the finite, whether it's optimal or not. What does that mean, optimal or not? Optimal means if it will find a solution, the solution will be optimal, is not. So answer would be yes and no both, depending on the situation. It would be yes if it is playing against an optimal opponent. So if the computer is playing against a very optimal player, then it is expected to find out the optimal solution. Another situation is no, it will not give you the optimal solution, where doesn't exploit the opponent weakness against the suboptimal opponent. So when there will be optimal opponent, that the, who is playing is not taking optimal action, then it will not guaranteed to give you the optimal solution. What is the time complexity? Time complexity is b k power m. You all know those things. B is the branching factor and E is the depth. What is the space complexity? Is the same as the breadth plus it is same as the DFS BM. So this is the depth first exploration, quite similar to that. Now, have you found out any problem with the algorithm? Problem in the sense, can we do better on the algorithm? Should we have to explore each and every node? What do you think about that? So that's what we need to think it. Yeah, so let me explain. You first see the last layer nodes, which is 80, 30, 25, 35, 55, 20, 05, and there is a number. So for 80, 30, what we'll take, mean we have to take, so it will be 30. For 25 and 35, how algorithm actually works, you need to understand. So for example, 80 and 30, when it was not there, 30 is not there, we just, what we do, we took the 80, we put it there. Okay, so root node, parent node is 80. Now we check there is a 30. We check whether 30 is the minimum than whatever it is or not. Yes, 30 is the lesser than whatever node it was 80, so we replace it, so now it becomes 30, right? So this is how algorithm works. So for 25, you see, we check the first left child, we saw this is 25, put it there. Now what we will do, we have to check it with the 35 and then see whether which one is the minimum and put it there. But do you think we need to see what is the other node, the right child? Because from there we need to take the maximum one, and the right hand side you can take, see there is a 30, so whatever the minimum would be, when it doesn't matter, right? Because finally we'll take the maximum one out of it, so 30 would be go to the upper node. So this 35 need not to be explored, so this is why we can prune it. This was the idea of showing this slide. Similar situation if you see for this right branch, we had 55 and 20. How we started, we took 55, we put it at 20, at the parent. Now we check with the 20 whether 55 is lesser than 20. No, then we replace it. 20 went there and it used to be there, right? So not replace, I should replace means changing both the term. I mean, if it is so, then it is not replacement. So it is copying the minimum at the parent node. So 20 would be there. Now for the next one, we have 05 and some number. So we put it 05. We can see the above node for 20 and 5 would be always the maximum one. So do you think we need to explore the right hand side? No, because whatever the number we will have either 5 or lesser than 5. But here we can see in the right hand side we already have 20. So 20 will go up above, right? So this node also need not to be explored. Out of 30, 20 we need to take maximum, then 30 would be go there, right? So this is how the algorithm works, if you see. So these nodes need not to be explored. So this, can we do pruning here? So this was the idea. Can we prune some branch which are not required to be exploited, so that we can do the computational saving there. This is the idea. Any question, any doubt till there? Please let me know if you have any question, any doubt till this point of time. We'll go further then. Okay, so we can go further. So this is a new term comes up with the minimax algorithm, alpha beta. So we are doing a modification into minimax algorithm, calling it as alpha beta pruning minimax, to save the time to do better on the time as well as this there, so and space as well, right? So we need not to do few exploration for few nodes in this situation you can see. So this 35, 30, we need not to be explored. So those things we can do, and then that's why we are going to the modified version of minimax algorithm called alpha beta. Let's understand alpha beta. What does that mean? The alpha beta procedure can speed up the depth first minimax search tree. Why we are calling depth first minimax search? Because if you see this one, it's quite similar to depth first search. We are doing depth first and then seeing the other branch and going upward like that. So this is why we are calling it the depth first minimax search. So in order to do better computation in space, we are doing the modification in minimax. What modification? So these two terms you please try to understand, alpha and beta. What does it mean? A lower bound on the value that a maximum node may ultimately be assigned. So for this situation you can see, for this one if you have to see, out of 30 we had and then we took the 25, the next node is the maximum which we are taking. So obviously we are quite sure that whatever the term will come here, which will be less than 25 here, right, because it is the mean node. So do we need to explore, because the upper node is the maximum node and we already have 30 which will go upward, so we are not requiring that number. So that's why a lower bound on the value that max node may ultimately be assigned. A lower bound, a value that may be assigned. What is the beta? Beta, an upper bound on the value that a minimizing node may ultimately be assigned. So this is the example if you see. So for this one, what would be the beta? For this one, the beta would be 30, because we can see on left hand side we have 30 and right hand side we have 25 or lesser than that. So we are quite sure at least 30 would be there, right? 30 would be there exactly. So beta, an upper bound on the value that a minimizing node may ultimately be assigned. So let's start this algorithm and understand what does that mean. So this is the problem, and alpha is what? Alpha is the base value for max along the path. Alpha is the max and beta is the mean along the path. So we started with that alpha. What alpha we can have maximum in the situation we are taking the we are initializing it with the minus infinity and beta as infinity, right? So the lower node we assign the same value, alpha is equals to minus infinity and beta equals to infinity. Now here we can see there is a 30, right? So what changes you are seeing, if you see carefully? So let's start with the downward. 80 and 30 we had. Obviously we'll take the minimum one. So what minimum we will have? Here we'll have the 30 and beta would be 30 here, because the base value for the minimum along the path. What is the base value here? You can see 80 and 30 will have the 30, right? First, now for this scenario we can see for the parent of this 30 node we have either 30 we'll have 30, right, and beta would be minus beta would be infinity. So now coming to 25, what is alpha and beta? What if you're going downward, we are just first copying pasting the terms and then updating the alpha beta. So we initially did it like alpha 30 and beta infinity. Now we updated alpha would be 30 itself and beta, you can see there is a number 25. So what would be the best value minimum along the path, which will be 25. So we put it there, alpha is equals to 30 and beta equals to 25. Whenever we find such situation where beta is lesser than alpha, lesser than equal to alpha, you just prune it. No need to require to go and search the subtree, because you are quite sure you are finding it here 25 you will have something 25 or lesser than 25, right? But you can see on the left side you are seeing the 30, and the upper node is the max one, then 30 would go there. Why you need to explore the further one? So this is where the situation come where beta is less than alpha, and then you are prune the subtree. So this is the effectiveness of, we are not going to search the subtree, so here time and space saved. So this is called alpha beta pruning. The same situation will also happen for this scenario. If you see, so 0, 5 and 65 were there, so you are putting 0, 5. Now you will have either 0, 5 or lesser than 0, 5, but the upper node is the max node, and in the right hand side you can see 20, so obviously 20 will go there, you don't need to explore further. So this 65 need not to explore. Here also this situation become true where beta less than alpha, and we're not going to explore those subtree. If you'll go above, the same similar kind of situation also occur at 15 node, where alpha become 20 and beta become 30. Beta become 15, and the situation gets satisfied, beta lesser than alpha, and then you are pruning the whole subtree. So see, this is quite a large subtree, and you are not going to check it. So your time and space both saved here. Intuitively, if you have to understand, how will you understand it? Why we did the pruning here? Because if you see the yellow subtree 15, 10, 15, 40, 10, 70 and 15, what will happen? The upper node is minimum one. So what it will go? Either 15 will go or minimum lesser than 15 will go. Perfect. But in the right hand side to the 15 you can see there is a 20, and the above node is the max node. So obviously 20 will go there, because something, if you have to choose max out of 20 comma 15 or lesser than 15, what it will come out to be? It will come out to be 20, right? So you need not to explore the right hand side. So that's why we prune the whole subtree. Now we'll try to understand what are the good scenario and bad scenario for alpha beta pruning. Will it work every time? Will it give effectiveness in every situation? Answer is no. It depends on the problem itself. In every situation it will not give you the effectiveness. There would be a situation where it not make any difference. The same effect, same time space would be required for minimax and alpha beta minimax. So there would be such situation there. So we need to analyze what are the best and worst situation for this. Let's understand that one. Yes, what will be the worst situation? So this is the C, 4 is the root, childs are 2, 3, 4. For 2, childs are 6, 4, 2, 7, for 3 it's a 7, 5, 3, So what will happen, and also we have written the what is the max mean and max mean, right? So for C, the lower one, we have 6, 5, 4, and the above one is the higher one. So we need to check all the things. 6, we put it there. We need to check 6 and 5. We need to check 6 and 4. Check 6 and oh, there were 2 nodes only. For 6, it was 6 and 5, right? So we put it 6 and we are checking with the 5. Yeah, 6 is greater than, we let it be because it's the max node. For 4, 3, 4 would go. For 2, 1, 2, 1 go. 1, 3, 7, what will go? 7 will go. So for this scenario, worst move encounter the first. Because you are not finding any such scenario where beta is lesser than alpha. You are not finding any such situation here. So there is no pruning at all. So this is where the alpha beta pruning will work as effective as minimax. Whereas the good scenarios where you have doing lot of pruning, good moves, it's simply ordered list. If it is ordered list, then you have something, right? If we can order the moves, we can get the more benefit from the alpha beta pruning. If it will be ordered list, then you will have the idea, because if 1 4 3 and you will have 1, and in the right hand side, let's say you have something 3 2 5, then you took 3, then you are quite sure 1 is the minimum here, and the above node would be 1 if it go upward, right? So this is the scenario where your good moves, ordered list will work better for the alpha beta pairing. So I hope you understood this, both the scenario, what are the worst move situation, what are the good move situation. Now we'll understand some crucial properties of alpha beta. Pruning doesn't affect the final result. This means that it gets the exact same result as does the full minimax. So it is only time and space is being saved. There is no difference in the solution what you are going to get. So this is the meaning of the first property. Good move ordering improves the effectiveness of the pruning. Pruning will not always work better than minimax. It depends on the situation. If there would be a lot of situations where beta less than equals to alpha, then you will do a lot of pruning, then your effectiveness should be high. But there will be situation where not a single case where this situation will satisfy, and in those scenario it will be as effective as minimax algorithm. With the perfect ordering, time complexity would be okay. So this is something you need to check. If you have to, if it is an ordered node, means it is in an order, and which is a favorable situation for alpha beta pruning, then what will be the time complexity? Time complexity would get reduced to b ki power m by 2. In general, what was the time complexity? In general, the time complexity was b ki power m. But if you do perfect ordering, then your time complexity will get reduced to half, which is b ki power m by 2. Double the depth search, right? So this is why it has been reduced here. A simple example of reasoning about which computation are relevant, a form of meta reasoning. A simple example of reasoning about which components are relevant. Okay, so what is the meta reasoning? Meta reasoning is reasoning about reasoning. So algorithm is thinking, finally thinking, and then it will take some action. So this is the meaning of meta reasoning. Now we'll have something called cutoff. Do you think we need to go below the few sub tree if we'll have some idea? Can we have some situation and say no, we are quite sure this is going to be solution, we don't need to go bit lower and explore more? Will it be some scenario? This is called cutoff. When you will be sure that you are going to very close to solution or solution, this, and there you decide, okay, I'll not run the algorithm further, I'll do the cutoff, right? So this is the scenario we are going to understand when to do cutoff. Let's understand this scenario. Evolution function for tic-tac-toe. So what is evolution function? Evolution function means evolution of a state. Evolution of a state means from that state what is more likely to win, right? So here for tic-tac-toe game, utility function is given a state, given a board situation, cross and 0, what is more likely to win by, let's say, cross. If we are talking about utility function of cross, how will you measure? As a human, what do you think, given the position, you think cross will win or 0 will win? How do you decide that? So how we decide is that how many possible situation it can go from that state which is resulting in win situation for cross. Let's say you are talking about the cross, this is the board situation, let's say. So board situation will be given. You are seeing both cross and zero position. So if I have to decide the utility function of cross, I'll see the situation and say from this scenario, how many terminal state it can reach with cross to win. Means how many times cross will be in diagonal, cross will be in horizontal, or cross will be in vertical, like that. I'll count, let's say 4, and also I'll count about the opponent for O, and it is, let's say, 2. So I can say utility function of this state is 4 minus 2, which is 2. So this is how they have defined here. Utility function is equals to RCDC minus RCDO, where RCDC is the number of rows, columns, and the diagonals in which computer could still win from the situation, right? And RCDO is the number of rows, column, and diagonals in which opponents could win. You are just doing the difference between these. So whatever I told, it is the same. Means a state would be given, and from there you think about how many terminal state could have cross to be win, right? Given the situation, let's say 7, not 7, not possible at all. So let's say 2 or 3, and for other you also need to calculate. So it would be for O, if you calculate it, it might be, let's say 1 or 2. Then you are doing 3 minus 1 or 2, which will be 2 or 1. So this will be the utility function for cross. Now how will we do? This was the tic-tac was the one of the simplest game, and we could easily figure out what will be the RCDO and RCDC, right? RCDC and RCDC. But for the complex problems such as chess, how do you decide from the given state how many possible terminal state it could lead to as a win situation? This is a very complex problem. For tic-tac-toe, very simple, small 3x3, you can easily figure it out. But for chess, how will you do that? So it is saying it's like a typically linear weighted sum of the features. So winning depends on how many features in chess. Let's say F1, F2, F3, and F4. What are those F1, F2, F4? F1 means how many units of players I have. It's not in chess only depends on how many players you have, what are their quality, whether they are queen, whether they are pawns, whether they are horses, and all those depends, right? So that also we consider. F2 is their impact, F3 is where they are, that also matters. So and F4, let's say how many elephants you have, right? So these are the 4 situations where you think in chess it depends who will win. So you do weighted sum of these features, W into F1 plus W2 into F2 plus W3 into F3 plus W4 into F4, right? And if this value would be high, then you can say the utility function for, let's say, computer is very high. From that state, computer will win. So this is the meaning of evaluation of function or utility. So for this one, it has given S is the state, and F1, F2, and F3 are the features, and W1, W2, and W3 are associated with these features are weight, which is saying importance of these features, right? So this is one scenario it is given. What is the meaning of F1? What feature it denotes? It says it is the features number of white queens minus number of black queens. If you are the white, you have the white color, right? How many queens do you have now, and how many queens have the opponent have, the black one, right? And the difference between them is just defining the feature F1, right? And the weightage of F1 is 9. It's quite high because queen matters, right? So that's why here it is given high weightage. Let's understand how we can do these are very, so this is the difference between traditional machine learning and nowadays whatever the machine learning we are doing different. We initially used to do all feature engineering. Finally we'll say and get it into computer, and computer will finally learn out of it. This was the F1, F2 and F3, and it has to learn W1, W2, W3 to fit the data. Fit the data means learn from the data. But nowadays we are not bothering about feature also. We are just giving the situation. Means even the chessboard, just a snap, and finally it will figure out the features itself implicitly. We don't know what it is finding, but it has been seen it is implicitly finding out the accurate features. If you go deep down and understand, it might be finding out the similar kind of features we are talking. Queens, how many queens white have, how many players it has, what is the situation, what are the position, those also matters, and it might have done similar kind of thing implicitly. But how do you calculate those things if there will be features? This is what is given. So we need data, right? And finally we expect that model will learn this importance. Importance is weight value, W1, W2, W3 and W4, right? So for example, this is one utility function is given 6k plus 4m plus u. How much king advantage you have, how many man advantage you have, m, and u means undenied mobility advantage, number of moves that max, where mean has no jump. So these are the different features of a chessboard which define dominance of a player. So this is how it has been formulated. Now what similar checkers players, there is a kind of algorithm. What it says how does A change its function. So let's understand what is the Samuel's checker player. It is a kind of algorithm which says when you are doing min max over chase, how can you do more effectively. So delta node equals to backup value node minus initial value of the node. What does that mean? Importance here, right? Backup value of the node minus initial value. If del greater than 0, then the terms that contribute positively are given more weightage to the terms that contribute negatively get less weightage. What does that mean? It means that you have W1, F1, W2, W3, F1, F2 and F3, right? Utility function. You have assigned some W1, W2, W3, right? Now given a scenario, if delta of node means backup value of the node minus initial value, if it is greater than 0, then you are thinking no, whatever the weightage I have given, it is not appropriately correct. I need to increase their weightage, increase their importance, right? So if it was W1, W2 and W3, you are making kind of W1 dash, which is equivalent to W1 plus delta into alpha something, right? Similarly for the other one, you are increasing that part. W2 are increasing, W3 are increasing, and also those who are positively contributing to the outcome, and those who are negatively affecting, you are reducing that value, so that finally it will go close to that. Delta should not be greater than 0, or it should be coming to close to 0. Then you can say your algorithm is quite accurate, because there is no difference between what you have hypothesized and the initial current value, right? No, whatever you hypothesize is current. If del is less than 0, let's assume the reverse situation, then the terms that contribute negatively are given more weightage. Yes, if del is less than 0, what does that mean? It means that you can see the del definition, backup value minus initial value. It is less than 0 means it will saying backup value is less than initial value, right? So whatever the backing value you are giving, it is less than initial value, then you need to you need to contribute. You need to what it is giving more weightage to the terms which are contributed negative, so that it will finally come closer to zero, and that's why you are maximizing the terms which is negatively contributing, and reverse also means those who are contributing positively, you are reducing their contribution. Now let's understand some additional refinement over that has been done over this thing. The probabilistic cut the branch probabilistically based on the shallow search and global level statistics forward thinking. It means that given the scenario, you are quite sure that from here who will win, right? Then you are probabilistically cutting down the branches which has not been explained, because you don't need more information about them, because you are quite certain about what is going to work. Those branches might not be that useful if your finally prediction whatever you're doing, it is quite close. It is quite, you have a lot of confidence over it. Opening and end games. What are the opening and end games? You know, when you start playing chess, it's kind of you have a kind of set of moves you have in mind. You play like that at starting, and in the end also it is like given the situation what moves you'll do, it is quite restricted. In the middle only you have lot of flexibility. You need to think a lot of times where to do, what to do, and like that. So this is what opening and end games. For some part of the game, especially initial and end moves, keep a catalog of the best moves to the make. So here you can kind of put a heuristics kind of thing. So what will be the open moves and end game moves, right? And in middle, let's algorithm to learn. Singular extension. Find the obviously good moves and try them at a cutoff. Now we'll solve few questions and we'll see. Do some workout with the examples. So till then, any question, any doubt about this, please let me know. Okay, so we can go further. So adversarial search problem uses, what it uses, there are 4 options. Competitive environment. Competitive environment means you and your opponent has different objectives. Cooperative environment means you and your opponent has similar objective, same objective. Neither competitive nor cooperative, only competitive and cooperative environment, both. So out of 4, what would be true for adversarial search problem? So just think for a moment and then as we started adversarial search, there would be some adversaries. There would be someone is going not with the objective. So obviously it is competitive environment, whether someone is playing opposite to your objective. So answer would be competitive. Next question, zero-sum games are the one in which 2 agents whose action must alternate and which utility value at the end of the game are always the same. Is it true or false? So that's we have to say about the zero-sum games. So what would be true? Will it be true or false? So let me discuss about the zero sum game. Zero sum game means I and my opponent is playing. At the any time the sum would be zero of RU20. If I am 15 at a score, he will be at -15. This is the definition of zero sum. Now you can say. True or false? So the statement is zero sum games are the one in which there are two agents, that's true, whose actions must alternate, that's also fine, in which the utility values at the end of the game are always the same. At the end of game are always the same. No, not exactly. I might end up at the -20 and 20, and in the other scenario it can be 30 and -30. So it's false. Utility values are always same and opposite. This is the definition of zero game. So answer would be B. Now next question. A game can be formally defined as a kind of search problem with the following components. What components will have in a game search problem? Initial state, successor function, terminal state, and all of the mentioned. It's quite easy. You can easily guess it out. It would be all of the mentioned. You will have the initial state. Will have the successor function. What does successor function mean? Given the state S, I can see I have three moves, A1, A2 and A3, and it will lead to S1, S2 and S3. Right, if I take S in A, it will lead to S1. If I take A2 in S, it will lead to S2. If I take A3 in S, it will lead to S3. Right, then we'll have three successors, S1, S2 and S3. Then I'll evaluate effectiveness there. What does that mean? Effectiveness, these are the known as the utility function. There will be terminal state. Terminal state means where you are ending up. Initial state from where you are starting. So all of three would be mentioned. So this is why the answer would be D. The initial state includes the board position and identifies the player to move. We already discussed what is the terminal state. This is what it is. The minimax algorithm computes the min-max decision from current state. Perfect. It uses a simple recursive computation of the min-max value for each successor, directly implementing the defining equation. The recursion proceeds all the way down the leaves of the tree, and the minimax values are backed up through tree as recursion up onwards. So this is how minimax work. This is treated whether it's true or false. Obviously it is true. Now next question, what is the complexity of minimax algorithm? Is it same as BFS? It is same as BFS, or space BM, time PM and space BM. Oh, I think it has missed one, something, power I guess. Otherwise option B and C would be same, BM and BM. Yeah. So let me correct it. Yes. What is the time complexity of minimax algorithm? Just think about it. What was the minimax time complexity, and then what was the DFS complexity? Is it same? This is the first option you can think of. And well, B option you can easily see whether it's a BF or not. BF is very less, so it's kind of not a BF, so it's not going to work. Same as BFS. Is it the same as the BFS or same as BFS? You need to think about it. So just think about it. Compare it. So what is the time complexity of Minimax? It is time complexity is BQ by M, if you remember. And space is VM, right? What about the DFS? DFS has the same time complexity and space, if you recall. So answer would be same as DFS, BQ by M, every time, and space would be VM. Now next question. So this is the situation is given, right? Minimax algorithm. Terminal nodes you have given there, right? So take this example, and the question is what would be the value of C. So terminal nodes are given -1, 4, 2, 6, -3, -5, 0 and 7. You need to go upward, which is maximize, then minimizer, then maximizer. So in that way you need to go till the minimizer, just minimizer, and say you will be able to find out C, and that value you have to say. So just work it out. Say what will be the C. Okay, so someone come up with the solution. What will be the value of C? So you just do whatever we how so -1 upper limit is the maximum. It will take just 4, because out of -1 4, which is the maximum 4. For 2 6, what will be the maximum 6? For -3 5, what will be the maximum? Maximum will be -3. For 0 7, what is the maximum? 7. Then D E F G you have, just fill out the upper node and say what will be the C. out of h and I, what would be the maximum here? You can see it is maximum is 4. So for d value would be 4. What about E? If you see maximum out of J and A, what you will have? You will have 6, right? So E would be 6. Now come to F. So for F there we have 2 child, minus 3 and minus 5. What is the maximum out of it? Maximum is minus 3 because minus the sign is there. So I have written minus 3. Okay. Now about G, you have 2 nodes 0 and 7 and you need to maximum out of this. What would be the maximum? 7. Which one path? It will be O. So we are putting in 7. Right. Now coming to B, you have to take minimizer. Out of 4 and 6, what is the minimum? 4. So this value will be passed for B. For E you can see it is 6, so it's not going to work. For B it will be 4. Now you have F and G, you need to take minimum out of it. So what will be the minimum out of minus 3 and 7? It will be minus 3. So this will be go up. So value of C would be what? Value of C would be minus 3. Right. Now if I have to take A also, we have asked question about C and the answer would be minus 3. Now I have to also see about A, which is maximizer. Out of 4 and minus 3, what is maximum? Which is 4. So A would be 4. What would be our answer? Answer would be minus 3 because it has asked about C. So we'll write here minus 3. Any question, any doubt? This part, please let me know. Minus 3. Step was minimum, simple. So we took maximizer from the below one and then minimizer for the second layer, second last layer, and we got finally minus 3 as C value. Any question? Now coming to the next question. So this is your next question, which is saying how the effectiveness of alpha beta pruning gets increased. So as I said, alpha beta pruning is not always good. There would be a situation where it would be as same as minimize, no change at all. But there will be a scenario where it will help. So it is asking on which scenario it will help. On what situation it depends. Option A depends on the most. Option B depends on the order in which they are executed. Option C, all of them, and option D, none of the above. So you need to say which one is the where effectiveness of alpha beta pruning depends. Just think for a moment. Then only we are going to win, otherwise we are not going to win, right? So that condition is satisfied with, right? Oh, so answer also I put it there. So what will be the answer here? So it depends on nodes. Because if it will be in that order, if it will be in ordered list, then you will have that condition get satisfied, and then you will be able to prune it. Otherwise, there is a scenario where it will not work at all. So it depends on the nodes itself. Now next question, which does the values of alpha beta search gets updated? Where does the value of alpha and beta search get updated? Option 1, along the path of search, initial state itself, at the end, none of them mentioned. So where the value of alpha and beta search gets updated, that you have to say. Whether it's along the path, or when you have the initial state initialization, there you see that it gets updated. At the end, finally, when you will have the terminal state, or none of the above which we have mentioned here, right? So we have to say which one will be there. And answer would be along the path. Along the path of search, as we traverse, we update alpha and beta. If you see in this example, that's what we're doing. Depending on the node value, we are updating alpha and beta. So here, next question is, to which depth does the alpha beta pruning can apply? 10 states, 8 state, 6 state, or any depth? In alpha beta pruning, there was nothing like a depth, constant depth, so it can work for anything. Next question, which of the following is or are true about minimax algorithm with alpha beta pruning? So for some statements have been given and asking which statements are true for alpha beta pruning minimax algorithm. Assume a two-player game where only outcomes win, lose and draw. So terminal state could be 1, -1 or 0. An algorithm is called complete if there is a way for the player to win and the algorithm finite. Completeness means that if their solution exists, then algorithm will find it. This is the definition of completeness. The notion of optimality is that it must find the sequence of least number of moves which carry to the win. It's not only about you are winning and finding out a solution, but that solution should be optimal. Optimality in terms of let's find the sequence of least number of moves. How many moves you are taking, in that you are optimizing, minimizing that move. So this is the two notions is given about. The first one is about the completeness, means if there is a solution, it will find out. Optimality means it will every time if a solution exists, it will find out, and that too optimal solution, that too in the minimum number of moves. So what is true about this algorithm minimax with alpha beta pruning? Option A, the algorithm is complete for a finite tree. We already read, yeah, it's true. The algorithm is optimal for finite tree. Worst case space complexity for the algorithm is OK bar Bm. Worst case time complexity for the algorithm is OK bar Bk bar M. So out of 4, which are the correct that you have to see. So think for us. First one is correct. The algorithm is complete. Now about 3, second question. about the second part, which is the algorithm is optimal for a finite tree. Third one is the worst case time complexity. So answer, obviously the first one I said it would be there. The algorithm is complete for a finite tree. No, it's not always optimal for finite tree, so this is not going to work. Worst case space complexity for the algorithm is OK per VM, and worst case time complexity for OK per VM. So do you think is it same as the minimax algorithm? No, every time would not be like that, but worst case here is given, that's why it is written. In the best case minimax, what is the best case time complexity for minimax with alpha beta pruning? Can anyone say what it was? It was O BK par M by 2, right? So just quite it's here it is OK par O BK par M. So there it reduced, but worst case would be the worst case, because you don't know the problem. Problem might be in the different. It's not a favorable situation to be given. Then what will be the running time complexity? So that is what does mean by worst case time, right? And it would be OK par O BK par M. Any confusion here? Any doubt? We'll go further then. The famous AlphaGo program defeated one of the best Go player, Lee Sedol, by 4-1. What key algorithm did AlphaGo use? This is the question. So AlphaGo game, you must have heard, it defeated the best Go player, Go is a game, by 4-1. What was the strength of AlphaGo? This is what it is asking. What would be the answer? Tell me. Yes, what are the strength? Also, you might not have heard about the AlphaGo program. So the main thing about the AlphaGo algorithm was this Monte Carlo search and deep neural network. So as I said, so in traditional machine learning you used to give features, but nowadays we don't require to stack features and give it to model. Model will itself figure it out. You don't have to give it to the model. Model will figure it out. So this is the strength of deep neural network. So what it is going, it will see the situation, it will see the board situation and find out the feature by itself. No one is going to say, given the situation, what important features are there and what you know strength upon. This is not going to be external information. It will implicitly find out by itself. This is the strength of deep neural network. And another important aspect of AlphaGo was there was a Monte Carlo tree search, and these two strengths which led it to defeat the best Go player, D-Sodal by large margin. So till we are good to go, right? So let's discuss the next question. In what situation would the minimax search not be the best algorithm in adversarial game? So it is saying minimax would not be the best algorithm in what adversarial situation? Option A, there is no opportunity to apply alpha beta pruning. The adversary is suboptimal. The search tree is not finite. The action space is continuous. So one already discussed there. If adversary is not optimal, you are not going to learn the best, because someone you are playing with and he is a very optimal player, it's most likely you will learn a lot of things compared to a person you are playing who is doing suboptimal. So this one is would be there, obviously, the adversary one, right? Other than that, what do you think would be there? The action space is continuous. So have you heard about that? No, till now we haven't discussed about that. What will happen if it would be action space is continuous? So we discussed about how. So answer would be this both, right? The adversary is optimal, the search tree is not finite. Oh, the search tree is not finite. If it is not finite, then any algorithm will not be complete. Where to stop and where to stop. No. The action space is continuous. Also, this is the situation where this is not going to work. Now, next question: mean max game is similar to what? DFS, BFS, iterative DFS, or not? If you see algorithm, we just when we start to discuss it is quite simple DFS, because we are going stepwise there and then going to the other branch and then doing exploration. So it is similar to DFS. Now assume that someone gives me a hint that the value backup at the root is the minimax tree is between 1 to 5. Can I use the information to my advantage? So if you have the information that the root of minimax tree would be in between 1 to 5, can you use that information? Can it be used? It's quite simple, you should come up with that, because minimax, how it works, finally seeing the child one, and whether it's a min or max, you are doing that operation over those childs, right? So if you have the information that your root lies between these two, and if you have 10 childs and you are seeing someone is not lying in between these range, will it help? Will this information that root would be between 1 to 5 is going to help that information in terms of alpha and beta? Yes, it is going to help, because you have this deterministic information that it is going to lie between 1 and 5. So alpha you can put it to 1 and beta you can put it to 5. Now next question, consider the game where it is known the value of leaf node can only be an integer between 1 to 5, inclusive. In that case, consider the game to be. Okay. So it is asking what is the value of what? This is a game where it is known that the value of leaf node can only be integer between 1 to 5. You have the information that all the leaf nodes are between 1 to 5, and that too inclusive. 1 can be there, 5 can be there. In such case, consider the following tree. Okay, we consider what value it is asking for. So it is not written. I remember it is asking for this node. Okay. What is the value of this node? Just try to calculate what is the value of this node. Means, if my cursor is not visible, let me say which node it is asking for. It is asking for root's first child from left. It is asking for this value. Please solve it out and let me discuss it. Think. Okay, let's discuss it. So let's start with leaps. The first leaps are 4, 4, 5, and you have to take mean. What will go there? For first one, it will go 4. Out of 5, 5, what will go? It will go 5. Now you have this 4 and 5, and this 0.2 and 0.5. 8 is given you kind of age weight or the probability. So what will be coming to the root would be their proportion, right? So here you have for first one 4 and for the second one 5. So 4 into 0.2 plus 5 into 0.8, right? So what it will come to? It will come to how much? It will come to 0.8 plus 0.8 plus 4, it is 4.8. The answer would be 4.8 for this one, right? Next question. For general graph, how one can get rid of the repeated nodes? You have the graph problem, and how can you get out of the repeated states? By maintaining a list of visited vertices, by maintaining a list of traverse edges, by maintaining a list of non-visited vertices, by maintaining a list of non-traverse edges. What will be the answer? It's quite simple. So do you think any relation with the A's is there? If you are asking about the nodes, repeated nodes or the repeated states, so there is no relation at all with the A's. So option B and option D are not going to work because there is nothing relation with the A's. Now you have by maintaining a list of visited nodes you are tracking, or C, maintaining a list of non-visited vertices. If you maintain the list of non-visited vertices, will it help? No, not going to help anyway, because it is asking for the repeated node. But if you save whatever you have visited, that is going to help. That if it will be in your taboo, then you can see you have visited there. You are again going to visit again. So option A would be correct, by maintaining a list of visited vertices. If you do that, then it is going to help you that yes, you have already visited there, so you can avoid that. Right, now next question. It is asking what is the final min max value which is backed up at the root node. So that you have to say what will be the value of A. The first layer after leaf node is minimum and then maximum. Right, then you solve it out and say what will be the value. Yeah, so I need to get the solution. So out of E, F, G, you have to take minimum, right? What is the minimum? 30. So B would be back up by 30. Let's solve it. So we put it here. We are solving. So if you are taking minimum out of this, then B would be how much? Because out of 30, 32 and 34, what is the minimum? Minimum would be 34. what about C? So you need to take minimum out of these leaps. What are those leaps? 18, 15 and 19. What it will come to? It will come to 15. Right? So 15 is there. Now about D, you have to take minimum out of 21, 15 and 10. So what it will go? It will go 10 there. Now A is the maximum. So out of 13, 30, 15 and 10, what will be there? It will go 30, right? So root not could be 30 will be the answer. So what will be the value of A? The value of A would be, if you see, the value of A would be 30. Why A would be 30? Because out of B, C and D, the maximum one is D and the value is 30. So that value is being backed up here. Right. Any question, any doubt, you can let me, we can discuss further.